In this lecture, we're going to continue with the topic on wave transformations. So what is the coastal nearshore environment like? In this case, we highlight that as the wave approaches the shallow water, it will undergo shoaling, and so this is a shoaling zone, and eventually the wave steepness increases to the extent of it exceeded the critical wave steepness, so we have a breaker zone. The breaker zone is where the wave dissipates most of its energy, but after this zone the wave will still have residual energy, so it will continue to propagate towards the shore in what we call the surf zone, and by the time it reached the shore and essentially almost lost all its energy, the last portion here is the swash zone. That is where the seawater run up to the shoreline, and of course it will run back down again in a repeated process along the shoreline. So how does the wave dissipate its energy in the nearshore region? Here we show different types of wave breaker. Assuming that all these are the same wave, for the same wave that approaches different shoreline, it may break in a different form. If the shoreline has very steep beach, like the first one here, then we may have a surging breaker. If the beach steepness reduces, we may get collapsing breaker, plunging breaker, or spilling breaker. This is an example of spilling breaker, which normally occurs in a relatively mild beach slope. It is characterized by foaming. Usually the foaming is a result of turbulence at the crest, and what happens is that the wave front will spread downwards and dissipate the energy steadily. In intermediate beach slope, we are likely to see plunging type breaker, whereby the wave will curl forward in a very pronounced manner. Here the wave curve forwards because the water particle velocity at the crest is faster than the wave celerity, so that it forms a tongue that plunges forward to dissipate the energy at the breaking point. The phenomena of plunging breaker is even more turbulent, and so it has the potential to generate even more irregular wave in the breaker zone. This slide here shows the progression of a plunging wave breaker. For higher wave steepness, the wave is likely to form a collapsing breaker due to surging effect. In this case, the collapsing breaker will build up, and then it will progress forward and progress steadily to dissipate the wave energy. Lastly, we have the surging wave breaker, typically observed in beach with high steepness or steep beach front. In this case, the crest builds up and surge forward, pushes forward, instead of a very violent wave breaking process. Previously, we looked at how the different type of breaker may occur at different beach, and now we want to introduce this breaker parameter, which relates the behavior more specifically. The breaker parameter C is given by tangent alpha over square root of h over L naught. Here alpha is the beach stiffness and h over L naught is the wave stiffness. So essentially, how the wave break or what type of breaker do we get depends on both the beach stiffness as well as the wave stiffness. Earlier we mentioned that if we have the same wave approaches different beach, they will break in different form. That's correct. In the same way, if we have the same beach but different incoming wave, each of those incoming wave have different stiffness, then they may also break in a different way. So spilling breaker usually is for C value in the range of 0.2, followed by plunging breaker in the range of 0.5 to 1.5, followed by collapsing breaker in the range of C equals to 3, and surging breaker for the value C in the order of 5. So basically, we can say for the same wave, if it approaches a shoreline with higher beach stiffness, then it tends to get surging breaker. If it approaches lower stiffness, it tends to get spilling breaker. On the other hand, for the same beach, if the wave stiffness is lower, it tends to get surging breaker. But if the wave stiffness is higher, it tends to get spilling breaker.